following video is on higher order derivatives. We have seen that the instantaneous velocity can be found by taking the derivative of the position function. So in other words, if the position is given by s of t, then the velocity v of t can be found by doing ds by dt, or in other words, s prime of t. So what is represented by v prime of t then? Well, remember, v prime of t would be the change in the velocity over the change in time, dv by dt. So when you drive, how do you change your velocity? Well, the answer is you push on the accelerator. So in physics, we call acceleration the derivative of the velocity, or the rate of change of your velocity over time. We represent it as a of t, and a of t can be found by taking the derivative of v with respect to time, so dv by dt, or v prime of t. But if the acceleration is the derivative of the velocity, and velocity is the derivative of position, then a of t can also be found by just taking the derivative of s of t once to get the velocity, and then taking the derivative of the velocity to get the acceleration. So in other words, we're taking the derivative of s twice. Let's look at an example. So if s of t equals negative 17t squared plus 5t plus 100, let's find a of t. S prime of t, we now are pros at. We bring the 2 out front from the negative 17t squared to get negative 34t, plus the derivative of 5t is 5, and the derivative of 100 is 0. So v of t is negative 34t plus 5. Now we can take the derivative of v of t to get negative 34, because that's the derivative of negative 34t, and the derivative of 5 is 0. So this gives us the acceleration a of t. Notice that all we did was take the derivative of s twice. In Leibniz notation, if we take the derivative of s once, we write that as ds by dt, and if we take it again, then we're applying d by dt to ds by dt. So notice that there's 2 d's in the top, and there's 2 dt's in the bottom. So we write this as d squared s by dt squared. This is the Leibniz notation for taking the second derivative. In Newton's notation, we have v of t is equal to s prime of t, and a of t is given by s double prime of t. And notice that we read this as s double prime of t. So in other words, if we want to find the acceleration, we just take the derivative twice of the position. We will see more uses for the second derivative as we move through the course, but for now, let's just practice taking second derivatives. So for example, if f of x equals 2x times cosine x, then we know that the first derivative is going to use the product rule. We'll take the derivative of 2x, which is 2, leave the cosine x alone, plus, let's leave the 2x alone and take the derivative of cosine x. So we'll get 2x times negative sine x. And if we wanted to take the derivative of that, well, we would have the derivative of 2 cosine x is going to be negative 2 sine x, because the 2 is just a coefficient, plus, now we have to take the derivative of 2x times negative sine x. So we take the derivative of the 2x, which is just 2, so we'll have negative 2 and leave the sine x alone. Now we need to take the derivative of sine x, leaving the 2x alone. So we'll have minus 2x cosine x. So notice that we've just taken the second derivative of f of x equals 2x cosine x. But we could also keep going. We could take the third derivative. So the third derivative I'm going to take the derivative of negative 4 sine x, so we'll end up with negative 4 cosine x, minus, now we're going to take the derivative of the 2x, leaving the cosine x alone, so minus 2 cosine x, and then minus, what happens when we take the derivative of cosine, we get negative sine x, so I'm going to get a negative negative, which gives me a plus 2x sine x. And once again, we can simplify this to get negative 6 cosine x plus 2x sine x. So all I did was combine the like terms. And there's no reason why we couldn't take a fourth derivative here. We're going to take the derivative term by term, so the derivative of the negative 6 cosine x ends up being a positive 6 sine x, because the derivative of cosine x is negative sine x, plus the derivative of the 2x sine x gives us 2 sine x plus 2x cosine x. And again, we can simplify by combining the like terms together. So notice that we could keep going forever just taking derivatives of derivatives. These are called higher order derivatives. The general notation for higher order derivatives, if y is equal to f of x, then the first derivative, we have 4 different ways of writing this. We have y prime, we have f prime of x, dy by dx, or d by dx of f. And these are all familiar notations for us at this point. So the second derivative is then written as y double prime, or f double prime of x, or d squared y by dx squared, or d squared by dx squared of f. The third derivative then is the same thing, but instead of squareds we now see cubes, and instead of 2 primes we see 3 primes. And the pattern can continue. The only difference is we don't want to write 4 primes, or if we wanted the 100th derivative we wouldn't want to write 100 primes. So what we do is as soon as we get to 4 we put round parentheses to distinguish it from exponents, and we write the number of times that we want to take the derivative. So if we wanted the nth derivative, we could do y and then superscript n in parentheses, or f superscript n in parentheses of x, or dny by dxn, or dn by dxn of f. So if s of t is the position, then we've seen that s prime of t is the velocity, and s double prime of t would be the acceleration. A new question is, what would s triple prime of t represent? Well, remember that s triple prime of t would be the change in acceleration over the change in time. So when your acceleration changes, how does that feel? You feel a jerk in your motion. So physicists called j of t the third derivative of s, so s triple prime of t. Here we see a comic where the little boy is saying hello to each of the derivatives, and when he gets to d cubed by dx cubed, the derivative is saying psh, whatever, and he calls it a jerk. A tough question, however, is what does j prime of t represent? And this is something I will not be talking about in this class, but it's a fun question to think about.